Welcome to the Explainer. Today we're cracking open a case file on one of programming's most elegant and, sometimes kind of misunderstood concepts, recursion. So, think about a super common task. You gotta add up a list of numbers. Your first instinct is probably just use a loop, right? Go through them one by one. But what if I told you there's a totally different way to tackle this? A way that could change how you think about solving problems altogether. All right, let's get into it. We need to introduce our main subject of investigation, the recursive algorithm. The name itself is a clue, right? It sounds like something that reoccurs, but how does it actually do that?
And here's the official definition. A recursive algorithm solves a problem by calling itself. Now hold on, because here's the kicker. It doesn't just call itself with the exact same problem. That would be an infinite loop. No, it calls itself with a slightly smaller or simpler piece of the original problem. It's all about breaking a big, tough challenge down into these identical, but way more manageable, bite-sized pieces.
And here it is out in the wild. This really elegant piece of code you're seeing is the rsum algorithm, and it's what we're putting under the microscope today. Just look at lines 3 and 4. The function rsum is literally calling rsum. That's it. That's the recursion, right there in plain sight.
So how in the world does this thing work? Well, first it asks a simple question. Is this array down to just one number? If the answer is yes, great. It just returns that number. We call that the base case. But if the array is bigger, it splits it right down the middle. And this is the cool part, it runs itself on each of those smaller halves. It just keeps splitting and splitting until every single piece is trivial, and then it puts all the answers back together on the way up.
This feels a little bit like magic, doesn't it? A function that just calls itself over and over to get a job done. But as investigators, we can't just rely on magic. We need cold, hard proof. So this is part 1 of our interrogation. How can we be 100% sure this thing is trustworthy? And maybe more importantly, how do we know it's not just going to run forever?
Okay, this brings us to the first major hurdle in our case. We have to prove that this process actually has an end. We need to verify without a doubt that it's guaranteed to terminate. Well, the logic here is actually pretty simple, but it's also incredibly powerful. With every single recursive call, the piece of the array it's looking at gets smaller. Every time. It's a one-way street towards simplicity. And since that problem size is always decreasing, it's mathematically guaranteed to eventually hit our stopping point, that base case with just one element. So, on that count, case closed.
So we know it stops. Great. But does it give the right answer? I mean, that's kind of the whole point, right? This is the second crucial test. And for this, we're going to use a really powerful proof technique that feels a lot like setting up a line of dominoes. It's called mathematical induction.
Think about it like this. There's no way we could check every single possible array of numbers. That would take literally forever. So instead, we're going to establish a chain of logic. First, we prove it works for the absolute smallest, simplest problem. That's like knocking over the first domino. Then we prove that if it works for any given domino, it's guaranteed to knock over the next domino in line. That's the chain reaction.
So our proof has 2 really critical steps. First up, the base case. For an array with just one number, does it work? Yes, it correctly returns that number. Boom, the first domino falls. Then we have the inductive step. And this is where we make a really powerful move. We just assume it works perfectly for any array smaller than the one we're currently looking at. If we assume that, all we have to do is prove that adding the correct sums from the 2 halves gives us the correct sum for the whole.
So yeah, this is the heart of it all, this assumption. It's called the inductive hypothesis, and it's the engine that drives the entire proof. It might feel a little bit like cheating, just assuming it works. But by assuming it's correct for all the smaller cases, we create this unstoppable logical domino effect that proves it works for every case, no matter how big.
Okay, so we've proven our algorithm is trustworthy. It stops, and it gives the right answer. But is it any good? Is it efficient? To figure out how much work it's actually doing, we need a way to see its every move. And for that, we need to call our star witness to the stand, the recursion tree. So what you're seeing here is a map of the algorithm's work. At the very top, that root of the tree, that's the whole array, the very first call to our function. That call then makes 2 new calls on smaller arrays, and those become its children in the tree. And this process just continues down the line until we hit the very bottom, the leaves of the tree, which are our simple one-element base cases. Now, let's take a step back for a second, because this is a huge insight. The actual numbers inside the array don't matter for the structure of the work. This tree you see here, it represents the exact same splitting process for any array with 7 elements.
A pattern is definitely starting to emerge here. The shape of the work is totally independent of the actual data.
And this is the master blueprint. This is the recursion tree for an array of any size, which we'll just call n. Every single one of those ovals or nodes represents one call to our rsum function. This abstract picture is what's going to let us analyze the algorithm's performance no matter how big the input is.
Okay, now for a really cool and kind of surprising piece of evidence. In a perfect binary tree like this one, if you have n leaves at the very bottom, how many other nodes do you have? You know, the internal ones where all the splitting and adding happens. The answer is always exactly n-1.
And that little factoid, that's the final piece of our puzzle. We know we have n leaves. We know we have n-1 internal nodes. With this crucial evidence in hand, we can finally calculate the total cost. So, what's the bill for all this work?
Okay, let's break this down. It's way simpler than it looks. We have n leaf nodes, and each one does just a tiny constant amount of work. Then we have n-1 internal nodes, and each of them also does a constant amount of work to split the array and add the results. When you add all that up, the total amount of work is directly proportional to n. Basically, if you double the size of the array, you roughly double the amount of work. We call this linear time, or theta of n.
And with that, the analysis is complete. All the evidence has been presented. So let's review the findings from our investigation and deliver the final verdict on our RSM algorithm. The investigation is a resounding success. We've proven that this recursive method is not just some elegant theory. It's reliable, it always finishes. It's correct, it always gives the right answer. And what's maybe most surprising of all, it's efficient. All of that complex splitting and combining adds up to a linear amount of work. In other words, it's just as fast as a simple, straightforward loop. Who would have thought? And this is why this whole investigation matters. The case file might have been about summing numbers, but the real takeaway here is the strategy behind it. Divide and conquer. Break a big problem into smaller, independent versions of itself, solve those little problems, and then combine the results. This mindset is a fundamental tool in computer science, and it powers some of the fastest, most important algorithms we have. So, we'll leave you with that final thought. Recursion isn't just a programming trick, it's a whole new way of seeing the world. Once you start looking for problems that you can break down into smaller versions of themselves, you'll start seeing them everywhere. The real question is, what complex problems will you solve with this new way of thinking?